We'll look now at some of my favorite problems for the CLEP exam, which are those involving counting. So let's look at what are called combinatoric problems. These problems, we're going to try to count the number of size groups of a given size from a larger set of elements. So let's look at the setup. So I'm going to be given n objects, and I want to understand how many groups of size k are there. The only question is, in my groups of size k, does order matter or does it not? So here is when order matters, doesn't matter. Here is when order matters. So in the case of order not mattering, the number of groups of size k that I can find from a group of size n is given precisely by this binomial coefficient. When order does matter, I have more objects to choose from. So I can actually look at a bigger number, which is n factorial divided by n minus k factorial, which is bigger in general than n choose k. So it makes sense, I think, that I would have more groups to choose from if order matters. All the groups that are the same up to order are considered one thing in the first case, but they're considered distinct when order matters, so I get more of them. So let's look at a few examples of this. A very simple example, I have 10 people at a dance, and I want to know the number of ways to choose groups of 2, to choose pairs. So clearly, n will be 10 and k will be 2. The only question is, in this scenario, does order matter or does it not matter? Well, I would say it does not matter, because once I choose a pair of dancers, it doesn't matter who was listed first and who was listed second. They're just dancing with each other. There's no hierarchy here. So we would say order doesn't matter. So I get number of pairs is equal to 10 choose 2, which is 10 factorial over 10 minus 2 factorial times 2 factorial. So 10 times 9 times 8, and so on. 8 times 7 times 6 is 2. So right, this is 8 factorial. Canceling things, I get 90 over 2, so 45. There is a bit of computation we had to do here, but I think the main work was in setting up the problem correctly. That what we needed to do was choose n, choose k, and decide whether order mattered or not. So let's look at another example. How many unique triples of letters exist if each letter may only be used once? In A, when I ask for unique triples, this means order matters. So I have n equals 26. This corresponds to the number of letters. And k is 3, because I want triples of letters. So order matters. So I get 26 factorial over 26 minus 3 factorial. And if you work this out, this is 26 times 25 times 24, which is equal to, I think, 15600. Now we ask if order does matter. I'm going to have fewer things, right? Sorry, if order doesn't matter, I'll have fewer things. So here n is still 26, k is still 3. Then I'll get 26 choose 3, which is equal to 26 factorial over 23 factorial times 3 factorial. And after a bit of calculation, you get that it is 2600. So quite a difference depending on whether order matters or not. Almost, well, not quite double, but fairly close to twice as many when order matters. In fact, 6 times as many when order matters. So it really is important to consider your problem and whether you should use the binomial coefficient, which is for when order doesn't matter, or just n factorial over n minus k factorial when order does matter.